if you remember me saying this, then it is absolutely true, and I made a mistake on this one, that the expected value of the random variable x is just equal to the integral from 0 to infinity of 1 minus, and this would be f of x, the cumulative distribution function of t dt. Now I said that, and then when for an example that I used, do you remember how this was verified, by the way? Just briefly, what he did was say that this is really equal to the integral from 0, you don't have to write this down, but I'm just going to give you the background. And it says that the probability, or it would be called the probability of x, or I'm sorry, of t itself, t here being greater than, or well, I should say, maybe I better not go down this route too far, but basically it's going to be the integral from 0 to t of the density function f of x dx, and then the outer one would be dt. Do you remember this? I was basically saying that if you do this, and then you change the order itself in the way the picture he has in the book, is if this is t and this is x, he's going to say if this is going to be dt here, and this is a value here, and this is x, so this is going to be dx here, and I guess x would be here. He's really going to say that I can change the order of integration, and I can go from x goes from 0 to t, and then from t itself goes from 0 to infinity. Do y'all remember this is vaguely? I don't want to go into too much detail because this is something that's drawn to the side. But if we do that, you'll get the actual definition of x, the integral of x, f of x dx from 0 to infinity. So what I did last time is a mistake. Remember that lower integral was 0. I had f of x here of x, or really, yeah, of x, the argument, equal to, and it is e to the minus, and here I had x minus 1, and it's only true for x greater than 0, and it gives rise to an f of x equal to 1 minus e to the minus quantity x minus 1, and this, I'm sorry, greater than 1, and this is true for x greater than 1. Do you remember this? And it's 0 else. Just show of hands how many do it. I know I'm talking a little fast, but I'm just trying to get to the point quicker. With me? Okay. So that means f of x of t would be equal to 1 minus, and I can do it this way, e to the 1 times e to the minus t for t greater than 1. Do you agree? Just a restatement. The only thing I did is factor out the, and this is supposed to be, I factored out that e to the minus 1 is e to the plus 1. I'm doing this for a reason, okay? Now, if you take that and you realize it's only good for t greater than 1, then I guess I can put this times u of t minus 1. We can forget about that because that's simply a step function. Do you agree? Now you come over here and you're going to realize this integral has two parts. When I integrate from 0 to 1, f of x is 0. Do you all follow me on that? With me? Because of that step function. It doesn't exist for t less than 1, right? So I get the integral from 0 to 1 of just 1 dt, and then I take that, and now I have minus the integral, and it would be from 1 to infinity of the quantity 1 minus that. So it's going to be 1 minus 1 minus e to the 1, e to the minus t, dt. And you can see the first part is going to be 1, And when you take this minus the integral here, you're gonna end up getting, I'll just tell you that in a nutshell, this is 1, and this part right here, last time we did, this comes out to be 1, and this is going to be plus 1 or 2. And you remember when you did the integration by parts, f of x dx, from, if you take a look at that, from 1 to infinity, you got to, how many remember this? I'm trying to just get through this quickly. Do you remember that? Now my point, the only reason for doing this, you can check this, it works. I did it and I think I posted it, didn't I? Did you all see it? The reason I'm saying that is getting the average value, if you have a density function, or if the density function is easy, the cumulative density function is easy to get, this may very likely be easier than f of x integrated. Follow me? That's the, oh, yes sir.
Sorry, why are you subtracting that second integral from the first one?
Well, see this?
Mm-hmm.
All right, so this would be this, right?
Mm-hmm.
So the formula is 1 minus that, right?
Mm-hmm.
Well, 1, right? What I'm really trying to say, this f of x that I'm subtracting is this entirety, right?
So if that second part is the 1 minus,
Well,
why are you
here's what I really should do. Actually, you're right, I should do it this way. It would be this, and then it would be the integral from 1 to infinity of the entirety of this, and I can put 1 minus f of x, and f of x here would be 1 minus e, and I can put it as just simply t minus 1 dt. Follow me?
so because of the 1 that's part of your original equation, you integrate from 0 to 1?
Well, remember, f of x of t is 0
Mm-hmm.
from 0 to 1, right?
Mhm.
From t argument.
Mm-hmm.
But the actual formula says you started in 0 to infinity, right?
Mm-hmm.
Well, from 0 to 1, that's 0. That's just integrating
Oh,
1 dt.
Okay.
That's all it is.
Okay.
Are you with me? Just making the point. I'm not saying you're going to use this, but I found when he puts a formula like that, it seems almost, who cares? But there is an application, and it's for some of the more complicated problems. I don't personally like integrating like x e to the minus 2x times some other function to get a value. But if you possibly can get an f of the cumulative density function easily, this is usually a doable one. So for what it's worth, I want to get that out of the way. The next thing I want to do is something I wish I would have done last time. And this is the problems involving series or parallel switching networks and finding the overall probability of them functioning or not functioning. You with me? Now this is important. So watch this and realize in his book he gives one very, I'd say, simple example, but he doesn't go into the complexities of it. So if I have just, I'll say this is going to be the sender and this is the receiver. And this is the way data travels, like so, goes that way. So if the probability of it working be P, this is P is probability of working of, I'll just call it working. Then 1 minus P would be the probability of it not working. Are you with me? Okay. If you have that leg is P, I'll call it P1, and we're assuming P is always the probability of it working. And then I have another leg here, P2, and I want to know the probability of the series event working. It has to be the probability of this working plus the probability of this working. Because if either one didn't work, it's a series circuit, it would fail. That's the reasoning, right? So the overall thing, this can reduce to simply, if this is sender and receiver, you can take that and just make it this. The actual probability of this working is P1 times P2. Does everybody understand? We're going to give a concrete example of this. This is 1-7.5, I think, but I don't remember the exact number. Do you all follow me on this? Now the extension is this. What happens if I go ahead and I say, now I have another leg, and you'll see this. And I say it's P3. And this is the receiver. And I want to equate it to this. What do you think happens? That's exactly it. And I can write a general formula to account for as many series links as possible. One thing you can see is the probability of it working keeps on going down. The more links in series. You all with me? Now we talk about parallel, because he didn't talk about the importance of this. If I have, here's my sender, and here's my receiver. And I'm going to say I have a path like this, I'll call P1, and a path like this, P2. So what's the probability of that actually have a connecting path? Now they're in parallel, right? This is what you always think of. Not the probability it works, but the probability it doesn't work first, all right? So if this is the probability of it working, then 1 minus P1 would be the probability of it not working. First, you agree with that. Gotta make sure you see this. And this one, the probability of this one not working would be 1 minus P2. Agree? Not working. Now, if this one doesn't work, but this one works, the whole system works, because they're in parallel. Follow me? And vice versa. This one works and this one doesn't work. The only way this thing cannot work is if both this one and this one don't work, right? And that probability of it not working, so I'm going to just say, I don't know, P bar not working would be 1 minus P1 times 1 minus P2. Do y'all follow me? That would be the probability of the system not working, which would be equal to 1 minus this that would be the probability of the system working. I didn't write down system working. How many understand what I'm saying? Agreed? Now here's the real point. That means I can take these two legs and say if I want just one leg from sender to receiver with a probability of it working, it would be that. And that probability is equal to simply 1 minus P1 times 1 minus P2. Does everybody follow me on that? We're going to give an example of it. I'm going to show you. This is almost guaranteed to come up on an exam or a quiz. Matter of fact, it is guaranteed. Not guaranteed. All right, does everybody follow me on this? Not this quiz, by the way.
So that's only for parallel though?
Yeah. That's series, that's the point. That series, that's parallel. Because you're going to see every possible combination of order, but I'm not done here. Now what happens if I extend this, and instead of having 2, I have another one? And you can see the natural extension. Well, what do I need to do? I'll call this P3. Probability of this one working is P3. Probability of it not working is? Right. 1 minus P3. Now the probability of this system not working would be the probability of this not working, plus the probability of this not working, plus the probability of this not working. Do you all agree with that, class? How many see this? With me? Now just think about it reasonably. If that's the probability of it not working, 1 minus that is the probability of it's working. What I'm doing is circumventing, going ahead and saying, what's the probability of this working, this not working, plus the probability of this working, and there is a huge number of things that are in that permutation, especially when you get 4 or more of these. But there's very few, there's, matter of fact, just one permutation of doing the not working. So the bottom line is the probability of that one not working would be 1 minus P3. And down here, the only thing you're going to do is have 1 minus P3 here. And that's the probability of it working. Can everybody follow me on this? Now you can extend this logically. Add another link. What am I going to do? Have another 1 minus P to the 4. Down here, I got 1 minus P to the 4. You all with me? It's much easier to do it that way. I'm just saying this right up at the top. And then you can think about, well, you know, he likes to do this. Well, what's the probability of receiving the one and transmitting one? And we can go through that. But the real thing you always want to find out is, I want to take an entire network and break it down to something like that, where I have one value. Then it's easy. Y'all with me, class? Then it's easy. Now I'm going to do an example in the book. And the solution's there. I think it's 1-7.5. If this isn't posted, this is from Cooper and McGillen. The reason I'm doing it, it's a simple problem, but it really showcases what I want you to see. And hopefully, you'll see it. While I'm erasing, I didn't check the weather. Is it supposed to rain at any point today or not? If anybody knows.
Probably.
It doesn't look like it.
Oh, fantastic.
Looks like clear skies. The rest of it, it looks like it may rain.
Well, I'm happy about that, if that's true.
I know, it's
hot though.
Now, I have 3 weather apps I'm just going to share. So I look at WeatherBug, I look at something called weather.com, and I look at AccuWeather. And I usually find AccuWeather is the most, I'd say, it has the highest probability of rain. If those two say 1 to 5%, AccuWeather say 30 to 50%. I don't know how they model this stuff. It's like the most, it's always going to go for the worst case scenario. It's very bad out there, but it doesn't matter worse. When I look at those and they all agree, I'm great. If it says blue skies, I'm not even worried. But if any one of those says something like over 50% rain, I get a little concerned taking an umbrella, because I've been drenched here more times than I care to talk about. Where it said basically no rain. Okay, here's the problem. I think, you tell me if I'm wrong, -7.5. And what he's got is something like this. Trying to draw this, right? I think that's it. And here's the sender, here's the receiver. And he's going to say he wants the probability of it working. Now, he does something that I usually don't do. He's going to say the probability, is that right, by the way?
I think, maybe I'm wrong, but I thought there was one arrow in the middle and then 2 points on the top and the bottom.
Well, there's a link to go this way and a link to go this way. I'm trying to show you 4, I've got 5 total links. So they're all the same probability of working. I normally don't do that, but I'm going to say this is just P working, P working, P working, P working, and P working, right? Now, if you were to do this problem based on what I told you, how would you reduce that to a single value? And by the way, what is that probability? Is it 0.9? Yeah. All right, so the probability here is 0.9, right? Now, I'm going to suggest this. Take the series ones and replace them with a single value. Y'all with me? Y'all follow me on that? So each of those series links has a probability of working of 0.9, 0.9. The probability of the whole thing working is 0.9 squared or 0.81. So now I can say this is really going to be 0.81 probability of it working. Then there's going to be still the middle one, and that's got a probability, I'll call it P1, of P2, and that's equal to 0.9 of it working, right? And then finally another one where it's the probability of it working is P1 or 0.81. Here's the sender, here's the receiver. And I might add, you should always put arrows in the direction of signal flow so you know, because some of these drawings, you'll have feedback or you're going to have it going back the other way. Make sure you just remember that. All right, now those are in parallel, right? So if they're in parallel, I know what I need is the probability of it not working, each one of those legs. This one is just going to be 1 minus 0.81. This one is going to be 1 minus 0.9. And this one is 1 minus 0.81. You agree? So I'm going to stop, make sure, but y'all follow me, my thoughts, my rationale. So the probability of it not working, I'll write it explicitly. Is going to be equal to 1 minus 0.81 squared times 1 minus 0.9. That's the probability of it not working. First, does everybody agree with that? Now, the probability of it working would be 1 minus that, correct? And that means this is actually the probability of it working. So that would be 1 minus, this is going to be, let's see, 0.19 squared times 0.1 squared, or 0.1. And I did this problem. What is that? Because I think the answer is right.
It's like 0.996.
Yeah, that's a rounded, yeah. Now, if you look in the solutions manual, he has a few more decimal, but it's right. You all follow? Now, if you remember what I showed you about parallel and series, these problems fall apart. They're seamless. What I warn you about is going down the route of the probability of this working plus times the probability, this not working, plus basically going the other route of every possible combination that works. It will take way too long. This is the way to do it. And in the book, he doesn't say this explicitly, which a little, I didn't see it in Chan's book, but this is the way to do that class of problems. Y'all with me? Now, anytime in the real world now, I'm just speaking from some experience, when you're dealing with multiple links, especially microwave links, you always are, at the end of the day, you want the probability of the system working. That's the bottom line. And you'll have all sorts of paths through in series. Do you know what the word repeater means at all? It means you take the signal you get, then you're going to go ahead and do some signal processing, get the base signal and amplify it and retransmit. A repeater is something usually in the middle of some sort of a distance between a sender and a receiver where you've got to amplify the signal to get to the next one, or it just can't go directly. So repeaters, the probability of working things like this are you multiply them. When you have repeaters that go any type of a signal where you have two paths to get to the final, then it's in parallel. So just keep that in mind in the real world. I don't know if you're ever going to experience that problem, but I can imagine you could. So that's this classic problem. And there's a lot of different ways to think about some of these problems. And if I know Chan, he'll find a way that's most complicated. And you don't need to make it complicated, at least in my opinion. This one's pretty good. Look, the way I showed it. It works every time, it's easy. So the next thing I want to do I've got to do these problems because they're classic problems. This is where you use odd and even functions to get the answer and circumvent a lot of anguish. So I think I gave you, this is out of the posted solutions. This is problem 2-2.4. And there was a mistake in the original problem statement. It should have been a sign and they had it as a cosine. So this is problem 2-2.4. And it shows you f, this is the cumulative distribution function of x equals 0 for x, and I'm sorry, for x less than -2, and it's equal to I think I did part of this at least. No, maybe I didn't. 1 plus the sine of bx here. And this is for x greater than -2, less than 2. And then it says it's 0 for x greater than 2. And let's see. First, he wants the values of A and B that will make that legitimate. And what else does he want? The probability that X is greater than 1. But first, do y'all remember, how many took a look at this one? Now, did it make sense? It's real important that at least you can reason your way through a problem like this. When you think about these cumulative distribution functions, really the f of x is really the integral. Technically, it's from minus infinity to any point x of f of x of, and I'll call it x prime dx prime. That's the definition. Now, if you look at this, what it's really saying, based on this, is anything below minus 2 is 0, and then it starts growing, and it grows at a rate of 1 plus the sign. So in some way, shape, or form, it's doing this, something like this. I don't know how to graph that exactly, but 2. And this would be the capital F of x of x. Y'all with me on this one? Here's the key point. F of x here is 0. F of x here, right here, is 1. That's the value that it comes in at, right here. And this is the value that has to be there. Now, there's something else I didn't say. But unless there are impulse functions, there can't be a discontinuation of f of x. It can't just jump arbitrarily. Only way it can do that is with impulse functions. Y'all follow me on that? So if there are no Dirac delta, whatever you call them, impulse functions is the term I use, delta functions, then you don't have to worry about any kind of discontinuities. This has to be monotonically increasing, and it can't have any discontinuities. So I know right here it's 0, and I think the solution, they had a, in the statement of the problem, they had a cosine there. Cosine will not work. It's a sine. So if you look at this, I know it's 0 at minus 2, so that would be a times 1 plus the sine of b, and this is minus 2. I'm going to ask you this right off the bat. How would you do it? Ask yourself. How do I, what information can I glean or get out of that statement right there? That's supposed to be a b minus 2b, to make it clear. Well, forget about a. Divide both sides by a, it goes away, right? So what do I know? I'm down to that point, right? And remember, sine is an odd function, or the sine of minus 2b is equal to minus the sine of 2b. Do you agree with that? Y'all remember this? Yeah, these are things that you're expected to understand completely. All right, so the only thing I'm going to do is this, at this point, I'm going to just change this and say this is really going to be minus the sine of 2b, correct? And that means the sine of 2b is equal to 1. Agreed? I come over here, and I know at this point, this is actually 1, not 0. That's on me. I know at 2, the cumulative distribution function is 1. So I know when x is equal to 2, I have 1 equals a, and then I have, if you look at this, I know that sine of 2b is 1, so I have, now it is 2b, right? So it's going to be 1 plus 1, and that means a itself is 1/2. Now that's the reasoning behind it. Do you agree with that? Now, if sine, I didn't say this yet, but if the sine of 2b is equal to 1, what do you know the argument here is? And always go for the lowest possible value in degrees. Don't go for the multiples, because you're complicating it unnecessarily. Well, sine of 90, isn't it? Is 1? Do y'all agree with that? Or sine of pi over 2? So I can say 2 times b must be equal to pi over 2. Let me stop. Does everybody follow my reasoning on this one? Agreed? I'm not trying to do anything where I just fly. I wanna make sure you see this, right? It's the reasoning behind how I get A and B for that definition of a cumulative distribution function. Y'all with me on this one? Okay, now that means B itself is pi over 4. That's my point. So now I have A and B. Or I can say between minus 2 greater than x less than 2, f of x is actually equal to 1/2 times 1, and it's going to be plus the sine of, and this would be pi over 4x, and then 0 else. Gotta make, yes sir?
Up there you have 1 is equal to A times 2.
Pardon me?
1 on the left side of the equal sign, is that because it's less than 2?
What are you talking about?
That one right there.
This says x equal to or greater than, you might say 2. It can be or equal to 2, right? So over here, this is a cumulative distribution function. At 2, it has to be 1 because anything beyond that's 1, right? So over here, it's 1. Then I have A, here's A, 1 plus, but I already found out sine of bx is 1. So that means A is 1/2. Is there something you don't see?
I see it now.
Is everybody clear on
Is
that?
that supposed to be x is greater than or equal to 2 in the problem declaration? Like where you have it equal to 1, where x is it supposed to be greater?
Where, help me.
On the left down, hold it there. Is that supposed to be x is greater than or equal to 2? Because it's just greater than. Or is there a discontinuity?
No, it's, you can have greater. It won't matter.
Okay.
This is not, there is no, it's not discontinuous, so whatever the value is just under 2, it's the same just over 2.
Okay.
It's, if we had a delta function right at 2, then it wouldn't, we'd have to distinguish it, but this has no delta. With me? Back to this thing. That's the function, and there were, I think the question was, what is, and it's 0 else, f of x, and here x equals 1, I believe. I think I just looked at it, that's where it was, right? Hey. Isn't that what he asked for? I really,
Yeah, it says found the probability that x is greater than 1.
greater than 1, all right, so this is the probability that it's less than or equal to 1, right? Can everybody follow me? That's what a cumulative distribution function means. So it being greater than 1 would be 1 minus f of x equal 1. I'll just put f of 1, right? Now you can see, if I'm going to do this, x is 1, so it'd be 1/2 times 1. Actually, let me do it this way. So this is really going to be equal to 1 minus, and I just put in 1 for my f of x here. 1 minus 1/2 times 1 plus the sine of pi over 4 times 1. I'm just writing this down so you can see how I'm thinking. Y'all with me? And if you do this, now I have 1 minus 1/2, or 1/2, and then I have minus 1/2, and then the sine of pi over 4, sine of 45 degrees, is 1 over the square root of 2, and that is, in fact, the right answer. I don't know the exact number, but that's it. Are you with me, class? So, and I think that's it for that one, right? I'm pretty sure. Want to make sure I did that one.
It's got one more, it just says found the probability that x is negative.
Okay, what's the probability? By the way, this is a great problem to see this. Look at this function. What's the probability if x is negative? It would be f of x equals 0, wouldn't it? Because that would be the probability is less than or equal to 0 is negative, right? Take a look at this. What is the sign of 0? 0. So it's a, right? A is 1/2. It's exactly 50%. It's 1/2. Just by observing this. There's something I'm going to get to next because it really showcases this. Okay. Now, remember, we have a density function. And if we have that, just listen, I'm not gonna do it right now, but if we had that based on what I said at the beginning of class, suppose you, calculators were forbidden, tables were forbidden. So what if I wanted the actual mean value of that function, f of x? We've got the distribution function, correct? Do you remember what I put up a second ago in the beginning of class? I know f of x, right? So I can say, well, tell you the truth on this one, I would have to accommodate it having negative values, probability. So I'd have to skew the integral, so it's probably better I don't do that. But it would be the integral of 1 minus that f of x with t in there. But then the integration would have to be over the range from 2, a minus 2 to plus 2, and I'm not going to go there because that's where I messed up last time. So it's easier, I think we're going to go ahead and get the mean, all right? So if you were asked based on that to get the mean of x, how would you do it? Mean. I'm going to give you a hint. If you look, you'll figure it out in a second. Now, so the mean of x would be an integral from minus 2 to plus 2, right? Now we know that's the possible range where the density function would be non-zero. Do you agree with that? And we can see by looking at this, what is the density function f of x based on this? And I don't want to spend a lot of time rewriting, but I want to just focus on one thing here. We know this would really be 1/2, right? And this would be my f of x. So what would the density function be? Do you remember how to get it? How many do?
The derivative.
Take the derivative of the cumulative distribution function with respect to x, correct, class? And what do you get for that? Well, you get the 1/2, right? I didn't put I better put the pi over 4 here because we've calculated that. And then you have to take the derivative of this with respect to x, which brings out a pi over 4, correct? Derivative of a sine is going to be a cosine, right? And here it's going to be pi over 4x. And this would be true for x greater than minus 2, less than 2. And it's 0 else. First, you agree with that. I want to make sure, I know I see people thinking, this is a great problem, because this is the kind of problem on a test I love. I can use one problem statement, I can get a whole lot of questions from that, and really just figure out if you know what you're doing or not. With me? Okay. Now, what type of function is this? Odd or even? Cosine. Cosine of x is cosine of minus x, right? That is a even function. This is even. Right? The expected value would be x. I'm just going to put it as f of x, right? dx. Do you agree with that? By definition. Do you agree? X is odd. This is even. Do you agree? Here's why you don't even need a calculator for this. So if I have odd times even, it is odd. So this is odd. Odd integrated from minus a to plus a is 0, right? The definition of an odd function is f of x is equal to minus f of minus x. So the integration below x equals 0 would be negative, or would be equal, or whatever. If it's negative, the integration from 0 to plus a would be positive, same magnitude, opposite sign, 0. You can mess with that one yourself, but it's true. So this is 0 without ever doing any integrations per se. You with me, class? Now that's a trick, and it's a nice one. The next part there is no trick for. If I wanted the mean squared value, how would I get it?
Square the x.
If I wanted mean squared, it would be this, right? Then you got to square the x. Now I'm just telling you this. Here, both, that's even and that's even, correct? Even times even is, so I can kind of reduce the complexity and go from 0 to 2 and multiply by 2. Do you follow me on that? Okay, I broke it down a little, but this is still not a trivial one. Now I got an x squared times all this crap. So I really have an x squared times a constant, the 1/2, and I have to integrate. That's not bad. That's x cubed over 3, right? But then I have an x squared sine of x. Now that's a little trickier. And that's where I wouldn't expect you to do that without a calculator, without, you know, a calculator can do this fairly easy. Does everybody have a calculator they're confident in that could do an integral like that? I mean, do you? This should be, you're engineers. If you don't have a calculator, you can do that, find one. It shouldn't be bad, but I would not expect you to do this by investigating odd and even properties, because you can't. The only thing you can do is simplify it like this. If I had to do it longhand, then what I would do is that sine function, I'd break it up to e to the plus j argument of the sine, minus e to the minus j argument of the sine over 2j, and then I have an x squared e to the ax dx problem, and I do integration by parts twice. It's a long process, but it can get the right answer. The manipulations of some of these things can drive you nuts if you're just trying to find a trick, identity trick, and there isn't one for this one that I know of at least. Okay.
Sorry, what's the 0 and the 2? I think I was right.
Remember, if it's an even function, right? For an even function, f of x is equal to f of minus x, right? So the integral from minus 2 to 0 is the same from 0 to 2, right? So the only thing I did is get rid of the lower integral and just go from 0 to 2 and multiply it by 2. That's the only thing I'm doing here, is trying to reduce the amount of work, if you want to think of it that way. Okay, that's that. One more thing. All right, finally, and this is the one I really want to get at. How do you get, if you have a function if you have a function, if you have x and you know f of x, and then you have a function of x we'll call y, how do you get f of y, the density function for y? So this is real important. I'm going to show you the simple way to do it. This class is over at 11, and I got 10:30. Is it 10:30 correct? 10:31? Okay, great. And I'll give you an example. There's one other trick. Denny, in the slides, he shows a method of doing it and thinking about it, but I'm going to show you probably an easier way to think about it. So here we're going to have a function, and I'm going to say I have y as a function of x. All right, and let's see here. How about if I say this is some f of x? All right. Now I'm saying, or maybe I shouldn't say f of x. I have y that's a function of x as such. But I know x, and I know f of x of x. Can you all follow me? So I'm saying I know the random variable x has it exists over a certain range, and I know the probability density function for that, or the cumulative distribution, because you can get the probability density from cumulative distribution, right? And I'm looking down here, and I'm going to graph x here, and I'm going to graph y here. And I'm just saying something like this exists. I don't know what the curve is. It doesn't really matter. But if you think about it, if this width here is, call it dx, and this is my f of x value. If you think about that, then over here, there's going to be some y value, fy of y, and make this thickness simply dy. You with me? Now the probability of f of x dx, what I'm really saying is I'm taking just a sliver of delta x thick, and I'm saying the density function, if I wanted to, the probability of that occurring x having the value over that range delta x thick, or f of x times that, is got to be the same as the probability of y dy. Can you all follow? That is the reason. In other words, whatever the probability is of x having a value, f of x is the probability density function times delta x here. It's the same thing. Remember, there's a coupler here between y is a function of x. It's got to be the same thing as the probability density for y having this value. You can think of it any way you want. A lot of times they do this. They'll say, like if I have y equals 5x, that's something like this, right? Straight line. So the probability of x having a value from 0 to 1 is the same as y having a probability from 0 to 5. That's what I'm getting at. You with me? And then you take it down to the differential, and you'll get the y, f of y dy times f of x dx. Now, why did I say that? Because if I look at this, if I want my f of y here, that would be equal to f of x dx here. And then you can see this is going to be divided by dy. And you can do it that way, or you can have f of x, and then you can divide it as dy dx. Now at this point, you need to make the decision. Instead of x, you want to put in y, so you might say that you're going to go ahead and x itself would be an inverse function, so it'd be what? Y to the minus the inverse of y. And let me give you an example of this so you'll see it. Basically, remember we have a relationship between x and y, a mathematical relationship. So down here, when you come to this point, the f of x, you take x and you replace it with the value of y. Follow me? And I'll give you an example. And then down here, you simply do the derivative of y with respect to x. Let me give you an example. I played with how to explain this better, so this is actually probably the easiest way to see it is with a clear example. This is going to be a linear relationship. We can do it with a squared relationship too, and then there's a little more complexity, but I'll get to it in a second. Now, in his book, I didn't look at the section on this, but this seems to be easier to do than doing the Leibowitz integration theorems and all those things. This gets to the point. So this is an exercise in the Cooper and Gillum. It's exercise 2-3.2, and it just says y is equal to, here it's 5x plus 3, and it gives f of x is equal to 5e to the minus 5x, and this you can just say is true, call it u of x. It's true for x greater than or equal to 0, and it's 0 else. You with me? Now if you look at this function for f of x right there, and it's legit, here, if this is x, and this is f of x, it looks like this. It would have a value of 5 here. Y'all with me? We want f of y out of there. That's the goal. Is how do you find the density function for y, knowing an equation that links y to x, using what I put up over there a second ago. So first thing I have to do is say over here, I need to find x in terms of y. So I have y minus 3 divided by 5 is x. That's the first thing. Y'all with me on this one? Now I come over here, and I remember that I had f of y, right, times dy, equal f of x, right? And then below there, I had dy dx. Do you remember this class? Just always start with f of y dy is f of x dx. Manipulate it from there. So the first, after that, I have to go in here and I have f of x, which is this, and now I have to exchange x for y. In other words, I want this to be a function of y. Everybody with me on this, class? We can't use an f of x for an f of y, so I come over here, and I see that's the relationship, so I come over here and I use this, and I said that would be 5e to the minus 5, and then look what x is, so x would be equal to y minus 3 over 5. Now there is a caveat, that's a u of x here, so that means it would be u of, and x is going to be y minus 3 over 5. In other words, now, does everybody understand what I've done? I'm going to put the full thing up first, and then I'm going to reduce the complexity. Try to at least. I'll divide that whole thing here by dy dx. Or you can take dx dy, it doesn't matter. So dy dx will be equal to simply 5. Isn't that right? First, I gotta make sure everybody sees this. Y'all with me on this one, class? So I'll come over here. This dy dx is 5. I'll stop for a second and let everybody read. Don't worry, I haven't forgotten about your quiz. You all with me on this? You'll get all the time you need. Everybody with me? All right. Now, I call it reducing the complexity, making it easier to understand. See those 5s? You don't need those. Are you with me? Can everybody follow me on what I did? Back there especially. Can you see this? What about here? I got 5 on top, 5 on the bottom. Agree? Agree. So I have this. I have minus quantity y minus 3. Now what about over here? I want you to reason with me. The only time a u function changes state is when the argument is 0, right? Will that 5 there change anything? Not in terms of 0, right? When y is equal to 3, that's where the 0 occurs. You can divide 0 by 5, it doesn't matter, right? This 5 does nothing. With me? Now what does that look like? Well, it looks like something that starts at y equals 3, right? And the height of it is just 1. As a matter of fact, this is a legitimate density function. And this is y. And so at 3, it has a height right there of 1. This would be my f of y of y. And it monotonically decreases like that. It looks just like e to the minus x. If x from 0 to infinity, that's what you basically done, is take that and skew it over by 3 spaces. How many see this? If somebody in this class asked me about the days for the mini semester dead days where we don't have class, did somebody, a reading, did you ask me about?
Yeah.
We do not have class on those days.
Okay.
We can't. And the reason is somebody could be taking a mini semester here and they need it for stipend. So I can't have you come in for class those days. We talked about that before, right? Okay, I'm just making sure. No. You with me on this one? Now, I better stop there. I'm trying to, did this lecture make sense? I'm trying to make it real clear, and I really don't want to use chant. Yes, sir.
So sorry, it's because, so you found dy dx is equal to 5, and then because you're basically dividing that function by 5.
Well, the way it goes is that's dy dx, right?
Yeah.
All right, that's 5.
Mm-hmm.
Put it in, it's 5, right?
Mm-hmm.
Here's f of x. I can't have an f of y in terms of x, so I replace x by what y is. The inverse, you might say, of f. Follow me? Here, I need to replace x, so I solve for x in terms of y, and I put it in there.
Oh, okay.
That's what I have to do to make this work. Y'all with me on this class? It's just taking the inverse. Okay. Do me a favor. Gotta do this row separation. How about fill this row up so you two